Okay, so this is the last prep talk, which is why the discussions start tomorrow. So Akashdwip will be speaking on Morava E theories.
Yeah, so I want to talk about E theory, and I'll start with kind of bit of basics. So let me. Oh, okay. And so E is a spectrum, and I want to have a multiplication from E smash E to E. So this is like R tensor R to R, and also there is a unit map. So this is the sphere spectrum to this guy. So, and they satisfy a bunch of conditions like associativity and so on. And also I want E to be commutative ring spectrum. So basically pi star of E is a commutative ring with respect to this guy. So now a definition. We say E is complex oriented, or CO, I'll write like that, if there exists a class XE in E2 of CP infinity, such that when you take this inclusion map CP1, which is just S2 inside CP infinity, in the cohomology, actually XE goes to this E2 of S2, so which is just pi naught of E, and this guy XE actually restricts to the unit map here. So XE goes to the unit in here. So then I call E to be complex oriented, and also by that I mean that there is a choice of orientation has been already mentioned, and there are some examples. So examples like you have HZ, Eulenberg-MacLane spectra, you have the complex K theory, you have this complex cobordism mu, they are all complex oriented. So now, so E is complex oriented, and by Atiyah-Hirzebruch spectral sequence, one can show that E star of CP infinity, this guy is just pi star of E, and then a power series ring in XE, and this guy will be pi star of E like this, and as CP infinity is just BU of 1, so I have a map from BU1 cross BU1 to BU1. So this is the map that classifies the tensor of line bundles over BU1. So this guy goes in the reverse direction, M upper star, and so yeah, sorry. To here, yeah. So this direction to this direction, and now let us look at this XE. This XE will go to a power series in here. So let us write that as f of XE and YE. So now, as XE is in degree 2, this whole expression, so let us write it Aij, XEI, YEJ. This expression should be in degree 2 as well, and this has degree 2i, this has degree 2j. So my Aij should be in pi of 2 of I plus j minus 2. So basically what we did, if E is any complex orientation, we choose the orientation and then we get a power series like this with every E. But this E actually, like this power series is not some random power series, it satisfies some certain properties. So let us see what are those. So formal group laws. So by a formal group law, I mean that an fxy in R of xy, where this R is actually graded, and again this looks like, so this fxy looks like something like this: aij xi yj, where degree of x is 2, degree of y is 2, and this guy, so aij belongs to R of 2i plus j minus 2. And this satisfies a bunch of conditions which are like this. So first, f0 of x is equal to f of x comma 0, which is x. That is the first condition. The second, it is symmetric. So f of x of y is f of y of x. And the last one, it is associative. This is the grading of this guy. This is the graded ring. It belongs to that degree. Yeah, like so here, like as I said, like you can think of R like as pi star of E. You get the same thing. Example like this. So f of x y y z f of x y and then z. So yeah, it is symmetric, it is associative, and this also follows. So if you basically take any complex oriented E, and this formal group law of that actually satisfies this. So yeah. That good as well. So yeah, now okay, so there exists a ring L which is graded and commutative, and so by FGL I would mean formal group law, that is the abbreviation. So there is exist an FGL mu L of xy belongs to L of x comma y, such that, so theorem given mu R, a formal group law over R of x y, there exists a map from L, a ring homomorphism map L from pi to R, such that this push forward, so mu of L is in here, so I take the push forward, mu L is actually mu R. So basically it says that every formal group law over a graded ring is classified by this ring L, and this is called the Lazard's ring. So now if you look at, so for example, I can take my E to be mu. So I can take my E to be mu, and the formal group law over that is mu of mu. So by this Lazard's theorem, I get an induced map L phi from L to mu star. And Quillen's theorem tells us that this phi is an isomorphism of rings. So okay, what does that mean? So basically it means that suppose now I take any R, a graded ring, and I have some mu R, a formal group law, I can view that R as an mu star module via this isomorphism. So basically what you're going to do, that given R and mu R, I can view them as mu star module. So like for example, you can take R to be like HQ star, you can take it to be Q star, and so on and so on. Any complex oriented guy, the pi star of E, you can think of them as mu star module. So yeah. Also another thing to notice is that there's the theorem that mu star is a polynomial ring in ZX1, blah, 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 like infinitely many variables. And each of these xi's decreases to I. Okay. Okay, now, so like it is known result. So result that if you look at, yeah, mu star x tensor mu star over q, this guy is HQ star x. And also there is this Connor-Floyd isomorphism, which tells us that mu star x tensor mu star of ku star is ku star of x. So now our question is like, so suppose I take any so basically this is the question, like, so is it true if I replace this guy? So if I take this functor x from the category of CW finite spectra and I go to x goes to mu star x tensor mu star and I take some mu star modular. So when can we say that this gives a cohomology theory? So like these two examples, I see that they give us a cohomology theory. So is it true in general? So for one, so for this functor, say f, to be this to be a cohomology theory, it has to satisfy those homology axioms. Like it has to preserve the, so I xi, it should go to mu star xi tensor mu star r, and then we know that this breaks into direct sum mu star xi tensor mu star of r. So this definitely satisfies the wedge axiom. But let us see. So another axiom is like I have to look at, so if x y to z, I have a vibration, this functor should also give me an exact triangle. So if I apply this f and I have this mu star x tensor mu star r to mu star x tensor mu star r to mu star z, this has to be exact. If this is true, then I can say that okay, x goes to this functor, gives us a homology theory, so it gives us a spectra. And one of the condition, like what can we impose on R such that this guy will be an exact functor? So one thing is, if R is flat mu star module, if R is flat mu star module, because this mu star x to mu star of y to mu star of z, this is an exact sequence, and if R is mu star flat, then definitely after tensoring with this still gonna give me an exact sequence. But if you look at this way, if you look at R as Q, so Q is not a flat mu star module. Ku star is also not a flat mu star module, but this still gives us homology theory. So what is happening actually? So to see that if I need R to be an mu star module, I am forcing that okay, they should, like tensoring with R should preserve every mu star module's exact sequence. But to have a cohomology theory, I just need R to be exact on this kind of mu star modules. So I don't need my R to be like flat over the total category of mu star modules. So now I'll restrict my category. So we will only consider mu star modules which looks like mu star x. And the thing about mu star x is there is an added action. So mu star x to phi, mu star mu tensor with mu star of x. So it has a comodule structure. It has a mu star mu comodule structure. So now I define my category. This is a subcategory of mu star modules. So this is the collection of mu star modules which has mu star mu co-module structure. So the objects are like that. The objects are mu star modules, which is also admits a map like this. Yeah, tensor over mu star. So yeah. So now let us. So yeah, so mu is this category of mu star mu comodules, and a map between them is basically, so if I have m and n in this mu, these are the objects. So m and n are mu star modules, and a map between them, say f. So it has to be an mu star module map as well as an mu star mu comodule map. So these are the morphisms. So this is the theorem of Landweber. So Landweber exact functor theorem. So let G be an mu star algebra. Actually, mu star module is good enough, but yeah, let us look at that. Mu star algebra, and then I take this functor m to m tensor mu star of G. So this again, this is functor from this category mu to again mu. So this is a mu star mu comodule. Then this guy is an exact functor if, okay, I should write something here. Okay. Yeah, fine. Isn't it? So mu star x is just this guy. So this is just pi star of mu smash x. So the derived smash product in the category of spectra. So this is a spectra. So you can take the pi star of that. That thing you denote by mu lower star of x. So this similarly, like this mu star mu is nothing but the pi star of mu smash mu. So now this guy m to m mu star G is an exact functor if xc minus 1 x of pn minus 1 is a regular sequence in G for all p in spec Z and n greater than or equal to 1. So this gives us a criteria when this functor will be actually exact. This is called the Landweber exactness. So now if you go back to these examples, we saw that, okay, Q is not flat over mu star, but is still giving us a cohomology theory. So it is an exact functor. Similarly, this Ku star, this is not a flat mu star module, but this is still giving us an exact functor. So actually, if you plug these two in, so if you take G, so let G be Q or Ku star Now you can see after doing this, so first let us look at Q, for example. So the action of mu star, so mu star acts on Q, and the action is given like this. This guy is Z, x1, x2, so on and so on. And then it acts on Q by, so the Z here goes to Z inside of this. So the Z goes inside Q, and this each of this xi actually goes to 0. Yeah. So now if you look at the regularity of these guys, so because now you have to quotient by this p, so q mod p, so which is 0. So the multiplication by these others is going to be monic individual. Yeah. And yeah, you can see that q is not an mu star flat, because if you look at this guy, so like you look at mu star to mu star, and you just take multiplication by some, say, x1. So this is an mu star module map, but upon tensoring q, this becomes q, and this also becomes q. But each of these xi's is 0 in here. So the map is just 0 map. So it was first an injective map, but now it is not. So q is definitely not a flat ring spectrum, a flat mu star module. But this gives us a cohomology theory because of this. It satisfies the Landweber exactness. Yeah, finite, but for all n. So these are the generators of this mu star. So mu star is a polynomial algebra in x1, x2, x3. So you first fix a p. So you have to check this condition whether this guy is a regular sequence or not in G. Or first you fix a p, and then you look at all these n's. So xp minus 1, xp square minus 1 to x of p to the power n minus 1. You do that. If it is regular, then this guy is an exact functor. So this gives us a homology theory. Mu star regularity. A G is an mu star module. So you can take, so basically like this, G to P to xp minus 1 dot 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 x of p n minus 1 minus 1. Then you just multiply with x of p n minus 1 to the same guy, whether this map is monic or not. That is the meaning of regularity. So you can check for both of these things, whether it is Q or HQ or KU star. No, first this is n minus 1, then I'm multiplying by x of p. Oh yeah. So anyway, yeah. So now, so we have answered, like, whenever, like if you give me an mu star module G, when this functor, so the question number 1 was, you give me a mu star module, so given mu star module G, when this guy is a homology theory. So that is answered by that. What is the reason? Yeah, so basically, I mean, for the proof, you have to go through this Landweber filtration theorem. So there is basically like the invariant prime ideals. So basically, invariant prime ideals mean prime ideals of mu star, which is also sub co mu star mu module. Okay, so like if I take and so mu star also has an action of this guy. So mu star to mu star mu tensor mu star. Okay, now if I take any ideal in between that in mu star, it doesn't mean it also will preserve the co-module structure. So it might not be a sub co-module. And if you take a prime ideal, the only prime ideals which are also finitely generated prime ideal, which are sub co-modules of mu star mu, these are like this. So for that reason, you need this guy. So far, I mean, I can say that, okay, I started with Q, and then I had a group law over that. So the formal group law over Q is x plus y, and this gives us an module structure over Q. And then I saw that okay, x goes to, because this is Landover exact, mu star x tensor mu star of Q is a homology theory. So what is this homology theory? This homology theory is basically HQ. Similarly, you can do the same thing with KU star. And if you take KU star and this group law, x plus y plus xy, and you do the same gymnastic and you receive another cohomology theory, another spectra. So which will be KU star, KU itself. So now I want to reverse the, continue in this process, meaning that, so question number 2, given an mu star algebra, say R, which is Landover exact, then I know that x goes to mu star x tensor over mu star of R. Now, because this is Landover exact, this gives us a spectra. So let us say that is at ER. So now I want to continue like mu star module and then consider get a new spectra. Like already we knew about these two spectra. Like we also knew what is HQ is, we knew what is KU is. So now the second part. So this is the second part, Lubin et spectrum. Okay, yeah. So we'll work with fields of characteristic P, and gamma is a formal group law over K, and also I would need that K is perfect. So basically X goes to XP is an automorphism. So for example, I would mainly just consider K as FPN, the finite field of order Pn. And yeah, so now a definition. That let F belongs to K of x comma y, and by f of x comma x, I abbreviate this guy as x plus fx. And a P series of a formal group law is again going to be a power series, but in just one variable, and that is defined like this: x plus f x p times. So I take an f and I take the P series of that guy, meaning that x plus iterated sum P times. Definition. Let f of x is in P of x if f of x non-zero. Say f is of height So given an power series in kx, basically, if I can write fx as this guy, so g of x p n, where g dash of 0 is non-zero, then I say that okay, f has height n. Okay, now you start with an f of xy in k of x comma y, and then you take the p series. So p series of f belongs to k of x. So by height of f, so height of f is defined to be height of pf. So I mean, it might not always exist. I mean, the p series might be 0 itself, but by if I say f has height n, that means p of f is like this, g of x p n. Definition again, let fg denote the category where my objects are like k comma gamma, where this k is a perfect field of characteristic p and this gamma is a group law of height n over k. So pair like this is my objects, and a morphism I k2 of gamma 2. A morphism exists when basically there is a field map, a ring map from k2 to k1 such that if you take the push forward I star of gamma 2, this guy is isomorphic to gamma 1. Okay, I'll define what is isomorphic, what is a morphism of two group laws are. So suppose you have f of xy and g of xy in x comma y. So a morphism in between them. So let us write it like f is a power series in just one variable, such that f of fx fy is equal to f of g of xy. So if that happens, I call that there exists a morphism in between them. And isomorphism basically if f is such that, oh, one thing is there is a condition that f0 has to be 0. There are no constant terms that is needed. If f is also such that f star of 0 is non-zero in k, so basically then we call f is an isomorphism of group laws. So my objects are like that. K1 is a field of characteristic P, perfect. Gamma 1 is a formal group of height n that I have written there. And I have a map from K2 to K1 such that I star of gamma 2 is isomorphic to gamma 1, meaning that there is an F like this. Yeah, meaning you just treat it as a variable, then expand. Like you kind of write it like Z. And for the exact kind of that reason, I need the constant term to be 0. Otherwise, you can't do the sum. In where? Yeah, like this. If is such that it is a group law, and then f dash 0 is 0 in k. I mean, then basically this means that if you take f, so there is, if f dash 0 is non-zero, a unit, basically then you can get another group law, say f inverse x, and you do the composition, then it will be identity. So meaning of that is that you get an inverse. Okay. Yeah. So now now there is a theorem that I have a functor from Fg, so this category Fg to spectra, so which basically takes my k of k comma gamma into E k comma gamma, and such that E k gamma is complex oriented. Yeah. So this is the kind of the main thing, main theorem is this. So given a k, a perfect field of characteristic P, you give me a gamma which is height n group law. From that I want to create a spectra which is complex oriented. So for example, we'll be looking at gamma which is Fpn, and there exists a canonical height n FGL, which is called the Honda group law, but basically there exists a guy like this, and the P series of this is just xp power n. So this is a height n group law over Fpn, and we will basically consider this Fpn gamma n goes to this E of Fpn gamma n, and I'll write it as En, and these Ens are known as this Morava theories. So first you fix a prime P, at each height n you get a cohomology theory En. So how does one do that? For that we need something called deformations of formal group laws. Okay, so by that I mean deformation of k comma gamma to a complete local ring B, and there is a maximal ideal, unique maximal ideal BMB, and by complete I mean that B is BM hat. So a deformation of k comma gamma to a complete local ring B is this information is a pair G comma I, where G is an formal group law over B. So G is basically a power series in B of xy, and the information is like this. You have K, so G of I, this I appears here. This is a map of fields from K to B mod MB. You have this B, the projection, and my gamma, the group law I started with, is here, and this pair G is actually a group law in here. So by deformation, we mean that, so gamma, you do the push forward, you get I star of gamma, which is isomorphic to pi star of G. Started with G here, like this. So by deformation, I mean this information of a group law. So also by, yeah, now this is, yeah. So now the category deformation gamma. So the gamma is this guy that I started with, and the B is this. So by this, I will define the category deformation gamma B, where objects are like G comma I, like this. So G is a group law over B, and I is a map from K to BMB. And a morphism from G1 I1 to G2 I2 is defined only when I1 equal to I2. Only then there is a morphism between them, and it consists. So the morphism is basically a map, a formal group law homomorphism from G1 to G2. So this F actually belongs to P of X, and such that you have this pi star of G1, which is pi star of G2, which is I1 star of gamma 1, which is I2 star of gamma 2. These are all same, and this F, pi star F, gives a morphism of this guy. So this is the unit map. Pi star of F of X should be X mod BMB. So we started with these deformations G1, I1, G2, I2, and my I1 is equal to I2. So these two guys are same. Because G1 and G2 are deformations, I have this thing. I1 gamma 1 is pi star of G1, and I2 of gamma 2 is same thing. So I have this. And this F, when you go reduction modulo MB, this just becomes X. So this is the identity morphism of these guys. Now, this category is a groupoid, and because like I started with this F to be an F is an isomorphism between G1 and G2, so I can invert them. So this is a groupoid. Deformation B is a groupoid, and I can take the classifying space of this guy, which I, by abuse of notation, I also write that. So classifying space of this category, I also write it as deformation of gamma B. So that's okay. Okay, now theorem Lubin-Tet. So the setup is the same. So gamma height is n, k is perfect. Then if this is given, like I have a k perfect gamma, then I can talk about this classifying space, which is a topological space. So the Lubin-Tet theorem actually states that pi 1 of deformation B I is trivial, it's identity. So, and for a classifying space, when you take the pi 1, basically, so I have to take also, I should write something like this, and D is something like G comma I. So D is a point in this topological space. So by pi 1 of this guy, we actually mean, I consider D in this groupoid. So this is just automorphisms of this D in deformation gamma B. So the Lubin-Tet theorem says that like, when you take this automorphism group of D, this is just identity. And it tells us that pi naught of deformation gamma Bi, comma D, this is the maximal ideal of this B cross n minus 1 times. And this n is the height of this guy that I started with. Also, it gives you some more information that furthermore, there exists a complete local ring E of A of gamma and a map an isomorphism K isomorphism from this maximal ideal in here because it is a complete local ring, and also and a formal group law F xy which belongs to E K gamma of x comma y, a formal group law here such which is universal deformation. So I'll explain this. What is this universal deformation? But basically it is saying I get with this K and gamma, if that is given, I get a complete local ring EK gamma, and there is a group law over that. And also K to this guy is an isomorphism. And when you restrict this F here, this is just the F you started with, this gamma you started with. So this says that, so you have K to EK gamma to M to EK gamma, you have this projection and you have this I have a gamma here, so which goes to I star of gamma, and I have an F, and this F comes from this Lubin-Tate F here, pi, so pi star of F. So in particular this EK gamma and F is also a deformation. Okay. So yeah, I have to explain what is this universal deformation means. So let us look at this diagram. EK gamma pi to K, and then you have a map I to B mod M, and then you have B to pi. So because all these are deformations, like we had the diagram, so I starting with F, then I goes to pi star of F, and by Lubin-Tate I know that pi star of F is gamma, and then I go to I star of gamma, which is pi star of G. So this is the information, because this is what classified the deformations. So now what do we mean by this universal deformation? This means that I can extend this diagram by a unique ring homomorphism, continuous ring homomorphism phi, such that here also I get pi star of F is isomorphic to G. So this is what it means by this universal deformation. So in other words, basically every deformation is co-represented by this guy, EK gamma. So okay, so now let K be again FPN, and this is the Honda group law of height n over FPN. Now then what basically EK gamma actually looks like. So we'll start with this wheat ring over FPN. So basically you have this is an nth extension of this PIDX to here. And basically what is the wheat ring is basically. So this is characterized by this property. Actually, so a wheat ring over a field, this is characterized like this. And this is pi. And if you have this, all of these are, this is a local ring, this is a local ring. So these maps are continuous ring homomorphism. Wheat ring is kind of universal in the sense that there exists a unique map which makes this diagram commute. So this is the wheat ring. And so now what we do is we just take WFPN to FPN, and there we take EK gamma to FPN, because from Lubin-Tate I know that EK gamma modulo the maximal ideal is FPN. So because of the universal property of Wittring, I get a map here, and also like the formal group law over this gamma n actually lifts to this guy here. So gamma n lifts to gamma n prime in WFPN such that reduction modulo m in WFPN gives us back this gamma n. So basically this means that if you look at WFPN, FPN, you have this gamma n prime which goes back to gamma n. So this is a deformation. So because of the universal property of this Lubin-Tate, I know this is co-represented by a map like this. And when you see the composition, basically this is identity. So I can say that, okay, WFPN sits inside this E of FPN comma gamma. So basically this guy is a WFPN algebra. And again from Lubin-Tate, you know that, so again, if you look at any deformation actually, you can consider that guy to be a WFPN algebra as well because of this universal property of Wittring. So form of WFPN continuous algebra, this map of E FPN gamma n B, this guy, because remember this actually co-represented the universal, co-represented all the deformations, and from the theorem we know that this is nothing but MB cross n minus 1, this guy. And so like it kind of prompts us to take EFPN because like EFPN already is a WFPN algebra. So what we do, we adjoin polynomials, and then if you look at this guy, so W1 to Wn minus 1, home of this WFPN, wherever this UIs goes, so because it is a continuous map, it has to go to this, each UI must go to some element in MB, and this homomorphism is like you can say what is this homomorphism is basically looking at the image of this W1 to Wn minus 1, so which gives you this, and because this ring is complete, so you have to take the power series. So this is E of FPN gamma n. Okay, and also I have to now tell you what is the formal group law, what this guy is. So yeah, so the formal group law X, Y, which classifies all these deformations basically. So this is again in EK gamma of X, Y, and this is actually defined as this. Yeah, you take X gamma. So this guy is in again K. So I've told already what this means, this symbol. So this is again defined as gamma of XY, and then you take this U1, and these UIs are again this polynomial variable that I've adjoined in EFPN. So U1 CP of XY, I'll explain what is this guy is. Gamma u of n minus 1, Cp of n minus 1, x comma y. And this Cpi of xy is actually 1 by p minus x of pi plus y of pi minus x of y pi. So this is given modulo, so this is congruent to this modulo this p u1 dot 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 u of n minus 1 square. So once you see this, now basically if you go reduction modulo m, remember the maximal ideal of this guy is generated by these things u1, u2, un minus 1. So if you go modulo m, you are killing all these guys, and then you get your x plus gamma y, which is gamma of xi. So that's why I said that when you go reduction modulo m, this f actually gives you gamma. Okay. Yeah, so now if you look at this guy, so I wanted to construct, I erased that. So I wanted to construct a cohomology theory, a spectra ek gamma, such that ek gamma of 0 would be this Lubin-Tate ring, right? And to construct that, I said I would use Landau-Weber exactness. And we have f of x comma y, which is in ek gamma of x comma y. But to get an mu star module structure on this, I needed this fxy to be in varying degree of r star, but this is just in degree 0. So what do? So I take u, which is a formal variable. So I take mod of u is 2, and then what we do is uk gamma, and you invert this guy. And now you define your f tilde of x comma y to be u of f of u inverse x, u inverse y, this guy. Now this is like what I wanted to get, because now the coefficients are in this r of 2 of I plus j minus 1, where my r is just ek gamma u inversion. So now I have a group law like this. So certainly what I can, so we have ek gamma as an mu star module so yeah, so let's say E of fpn gamma n, this guy is the Wittring wfpn, and then you have un minus 1, and then have adjoined another variable, and this is mu star module via f tilde, which is u f of u inverse x, u inverse y, so things like that. And now the theorem is wfpn u1 to u of n minus 1 u plus minus 1 is Landau-Weber exact. So this guy is Landau-Weber exact. In other words, if you look at this functor x from this category of CW finite spectra to mu star of x, then you write like this. star is homology theory. Denote as En, and this En is known as the Morava theory. Yeah, stop here. Yeah, so basically, like you start with any deformation. So what does that mean? You have a B, there you have a G and an I. So K from I to B mod M, you have a G such that this thing happens, except this guys. So there is no arrow a priori. By universal deformation, so if you look at this guy, Ek gamma to K and the group law over this is also a deformation of K comma gamma, right? And by universal, I mean that there will be a unique ring map from this direction to this direction, say phi, such that F push forward of F will be isomorphic to G. So in other words, basically any deformation is classified by these maps from Ek gamma. So you start with some deformation B, that is like you get a map from here to here, and such that G is actually the push forward of phi star. In that sense, it is a universal deformation. It classifies all the other deformations.